Chapter 5.4 is going to be sampling distributions and the central limit theorem. So for this chapter, what we've been doing is essentially studying the relationship between data entries or data values, the x values, and the mean mu of the population. Now we're going to be studying the relationship between the means of samples from the population and the population mean. So it's going to be the relationship between the mean of samples and the population mean. So remember that x bar represents a sample mean because that's what we'll be using a lot for this section. So this first page is going to be pretty confusing. Hopefully the next page will clear it up. So a sampling distribution for the definition here. A sampling distribution is formed when samples of size n, so they're all the same size samples, are repeatedly taken from a population with replacement. So essentially, a sampling distribution is when we take samples of the same size, every possible combination of samples of the same size from a population. So some properties that we will be using on the next page and going forward. The mean of all of these sample means, so it's the mean of sample means, which we can denote with a mu sub x bar, equals the population mean mu. And the standard deviation of these sample means, which is also called the standard error, we can call sigma sub x bar, is equal to the population standard deviation sigma divided by the square root of the sample size. Okay, so probably pretty confusing. Let's take a look at an example so hopefully it clears up what this means. So let's list all possible samples of size 2 with replacement from the population 1, 3, 5, 7. So here are our data entries, whatever they represent, 1, 3, 5, and 7. Then we're going to calculate the mean of each sample, and then we're going to find the mean, variance, and standard deviation of those sample means. And we are given the mean of the population, which wouldn't be that hard to find. It's 1 plus 3 plus 5 plus 7 divided by 4. That gives us 4. We could calculate the variance and get 5. And then standard deviation of those 4 numbers would be the square root of the variance, which would be the square root of 5. Okay, so let's do fill in this chart here. So this chart, what this is going to be, this is going to represent the sampling distribution of sample means. Okay, so we want to get every sample of size 2 from that population 1, 3, 5, 7. So it is with replacement, which is pretty key here. So we can take a sample of 1, then we can put it back and pull out another 1. We can take a sample of 1, put it back, and then pick out a 3. And then we can pull out a 1, put it back, then a 5, and then a 1 and a 7. So there's 4 of them so far. So next, 1, 3, 5, 7, we could pull out a 3, put it back, pull out a 1, 3, put it back, pull out a 3, 3 and a 5, and then 3 and a 7. And then we can do 5, 1, 5, 3, 5, 5, 5, 7, and then lastly, we would have 7, 1, 7, 3, 7, 5, 7, 7. Okay, so all this is samples, and they're all sample size 2. It's every possible combination of a sample size 2 from that original population on the top right of the screen. Okay, so now let's calculate the mean, the sample mean of each one of these samples. So when we calculate the mean, we just add them up and divide by 2, right? So it's going to be 1 plus 1 divided by 2, which is clearly 1. The mean of 1 and 3 is going to be 1 plus 3 divided by 2, which gives us 2. The mean of 1 and 5 gives us 3. The mean of 1 and 7 gives us 4. And then I'm just going to fill out the rest of these. 1, 3 is 2. and then 3 and 4. And then it's going to be 5 for the mean of 3 and 7. And filling out the rest of them, we get these values. And 4, 5, 6, 7. Okay, so all of these values here are just the means of the sample to its left. So let's take the mean of all of these numbers. So I'm taking the average of this right column, which is the mean of the sample means. If we add all of those up and divide by how many there are, we're going to get a value of 4. So let's take a look back at what was given to us here. We were told that the mean of the population was 4, so they're actually equal. So the mean of those sample means equals the mean of the population, which was told to us in the previous page right here. So we just kind of showed what that meant. And now let's just find the standard deviation of the sample means. Let's find the let's find the variance first. So here's the variance. Actually, just kidding, let's do the standard deviation. So the standard deviation of all these numbers for the sample means, we could go through and do the calculation for standard deviation if you remember that. Let's actually use the shortcut from the previous page. We're told that the standard deviation of the sample means is the population standard deviation divided by the square root of the sample size. So it's going to equal this, which these are given to, well, this is given to us. Sigma, the population standard deviation. So that's going to be radical 5 over the square root of n. The square root of n is going to be, n is the sample size of each one, which was 2. So this is going to be about 1.581. And now let's find the variance. The variance is just going to be the standard deviation squared, which is 1.581 squared, which is about 2.5. Okay, so the important thing here is not so much the variance, but the mean and the standard deviation. Okay, so next for the central limit theorem. So the central limit theorem is actually one of the most useful and powerful theorems in statistics. So it says that a sampling distribution of sample means, which is what we just did, for sample size 30 or greater, can be approximated using a normal distribution for any distribution. So it's so powerful because we can do this even when the distribution of values for our data set is not normally distributed, which we could not do previously. And in general, the greater the sample size, the better the approximation. So this means that we can relate any distribution, no matter what shape it's in. If we thought of it as a frequency histogram, we can relate any distribution of sample means to the normal distribution, which means we can use the z-tables, z-scores, and all that good stuff. So let's see an example here. So let's say we had any population distribution here, and let's say it looks something like this. So that's clearly not normally distributed, right? Because it's not the bell curve. And let's just say we happen to know the mean, though, of this distribution. Let's say the mean is about right here, whatever that is. And let's say that the standard deviation would be here. So this would represent one standard deviation to the right. So this would not be too much help. We can't use the z-table. We can't find the z-score because it's not normally distributed. But what we can do is do what we did on that previous couple pages ago, where we find the sampling distribution. If we were to graph the sampling distribution, it would be normally distributed. So it would look something like this, the sampling distribution of sample means. So imagine once again that we created a frequency histogram of it, and then we put this over the top of it. So this right here would be the mean of the sample means, which we know equals the population mean. And one standard deviation away would be about right here again, just like it normally is, right at that inflection point in the curve. So this would be one standard deviation away, where that standard deviation of the sampling means equals the population standard deviation divided by the square root of n. Okay, so definitely pretty conceptually confusing. Hopefully that kind of cleared it up. So let's look at an example here. So let's say that cell phone bills for residents of a city have a mean of $47 and a standard deviation of $9, and a random sample of 100 cell phone bills are drawn, and the mean of each sample is calculated. We want to find the mean and standard deviation of the sample means and sketch the sampling distribution. Okay, so let's say we have the graph of the cell phone bills, and let's say they look something like this. So this would be the graph for the distribution for all cell phone bills. And notice that the way that it was drawn here, it is not normally distributed. So we can also see that the mean, we said the mean was 47. And the problem also told us that the standard deviation was 9, so that would be one standard deviation away right there. So not normally distributed, so we can't do anything using the normal distribution. So now let's take a look at what the distribution of the sample means would be. So this would be normally distributed, and we also know that, so over here a little more, we also know that the mean for the sample means is equal to the population mean, which was 47. And let's figure out the standard deviation for the sample means. We know that that formula is sigma over the square root of n. It told us that the standard deviation for the population was 9. N is right here. It said it was sample of size 100. So divided by the square root of 100, that's going to be 9 divided by 10, which is 0.9. So we can actually fill out that horizontal axis now. And it would look something like this. So notice that I labeled it as X bar instead of X because it's the mean of these 100 cell phone bills. And the mean, we set the mean of those mean cell phone bills was 47, which we have right here. And I also added and subtracted one standard deviation. So it looks something like this, where this right here is our sigma sub X bar. Okay. So we can see that the distribution of sample means is normally distributed, which once again means that we can end up finding the z-score for this and using that z-table to help us solve certain problems for it. Okay, so let's do an example here. So it's probability and the central limit theorem. So like we just mentioned, we can actually calculate a z-score here. We can transform a sample mean X bar into a z-score using this same formula from before, but it's tweaked just a little bit. So instead of X, instead of individual values X, we're using the mean of the sample means. Or sorry, we're using sample means, which is X bar. So it's going to be Z equals X bar minus the mean of the sample means divided by the standard deviation of the sample means. So we know that the mean of the sample means equals the population mean. And then we also know that the standard deviation of the sample means equals the population standard deviation divided by the square root of the sample size. So the formula is a little bit different. Other than that, we're almost doing the exact same thing though. Okay, let's do two examples here. So suppose this table consists of the average time different age groups spend driving each day. Answer the following questions. Assume the population standard deviation is sigma equals 1.5. Okay, so we have this age group column on the left, and then the time they spend driving on average each day in minutes. So for the first question here, we have if 50 drivers are randomly selected between the ages of 16 and 19, which would be this first one, what is the probability that the mean time they spend driving each day is between 24.7 and 25.5 minutes? Okay, so what the question is asking is it wants the probability that the mean time they spend driving is between 24.7 and 25.5. So remember, we're dealing with means, sample means, so it's x bar instead of x. So this is the problem that we're trying to solve here. So remember, it looks exactly just like we did previously. So a couple things we have to take into account. First, we have to make sure that n is greater than 30 in order for us to be able to use the central limit theorem. So it is greater than or equal to 30, so we're good. Let's figure out some of the givens here. The mean of the samples. So the mean of the sample means is going to equal the population mean. So this is going to be from the table. This is going to be the 25 minutes. It's the mean of the sample means for that age group. And the standard deviation of the sample means is going to be sigma over the square root of n. That was given to us in the problem. It said sigma was 1.5 and n was 50. So that's going to give us 0.212. Okay, so the reason why we need these is because we have to find the z-scores for 24.7 and 25.5. So let's do that down here. So finding these z-scores for 24.7, we just have to remember that we're using the correct z-score formula. So it's x bar minus mu sub x bar over sigma sub x bar. We're going to plug in our values here. That's 24.7 minus 25 divided by 0.212. That gives us a z-score of negative 1.41. Okay, and then we have to do the same thing over here for 25.5. X bar minus mu sub x bar over sigma sub x bar. And we plug everything in, and we get 25.5 minus 25 over 0.212. That gives us a z-score of negative, or positive, it's positive 2.36. Okay, so what this means is that the original problem up here is actually going to be equal to the probability that the z-score, that z is between those two values. So we put down their corresponding z-score right below them and put a z instead of an x bar now. And now we do this the same way that we've done it. It's going to be the area to the left of the larger one minus the area to the left of the smaller one. So this is going to be looking at the table now. So I'll put a little note from table. Okay, so from the table, the area to the left of 2.36 is going to be 0.9909 minus the area to the left of negative 1.41. That's 0.0793. So we subtract those, we get 0.9116. Okay, so about 91% chance of this happening. Okay, and now for the next part, if 40 drivers are randomly selected between the ages of 25 and 54, what's the probability that the mean time they spend driving each day is more than 63.5? Okay, so once again, let's make sure that n is greater than or equal to 30, which it is because it's 40. So we can do this method. If it wasn't, we wouldn't be able to do it. And the mean of the sample means is going to be the population mean, which is the value on the table. So this is for between 25 and 54 age group. So 25 and 54 is going to be right here. That's going to be an average of 64 minutes. So that one is going to be 64. And we need to calculate standard deviation of it, which is sigma over the square root of n. Sigma, once again, for the whole problem was 1.5, and n here was 40. So 1.5 over the square root of 40, which is 0.237. Okay, so we are looking for the probability that the average time is more than 63.5. So that's going to be the probability that x is greater than 63.5. So that's our whole problem here. So we have to find the z-score for 63.5. So it's going to be z equals x bar minus mu sub x bar over sigma sub x bar. We're going to plug everything in. That's 63.5 minus 64 divided by 0.237. So all of these values were from what we wrote in red right above. That's going to end up being negative 2.11. So now it's like the same thing that we've been doing. This is going to be equal to the probability that now z is greater than that z-score. Since this is greater than, we have to do 1 minus the probability that z is less than in order to use the table, because that's what the table tells us. So we look up the area to the left of negative 2.11 on the table. That would tell us that it's 0.0174. We subtract those and we get 0.9826. So there'd be a 98.26 or 98.26% chance of this happening. Okay, so that is it for this section.